Hello, today we are going to be working on finding limits when direct substitution doesn't work. Specifically, we're going to be looking at gaps, which are also called removable discontinuities. So the question of the day is, how do you evaluate limits when f of x has a discontinuity? So we're going to get started with an example. We're going to take the limit as x approaches 2 of the function x squared minus 4 over x minus 2. Now we're going to follow the first method of finding a limit, which is direct substitution. And we're going to go ahead and substitute this. And you're going to find that you get 4 minus 4, which of course is 0, divided by 2 minus 2, which is also 0. This is a familiar expression. 0 over 0 is not undefined necessarily. It is called indeterminate form. Indeterminate form simply means we cannot determine the value at that point. And just because we cannot determine the value at x equals 2 doesn't mean that it doesn't have a limit. It actually means that we are not able to find the limit with direct substitution, but what we can do is more math. So every time you see the expression 0 over 0, we're going to do more math. From the beginning of class, we actually discussed what this means. You should recall that 0 divided by 0 is not only indeterminate form, but it also happens when you have a gap. And so we're going to just do a little bit more math to try to find this limit. And what kind of math are we going to do? Well, if we look at the expression, it seems kind of intuitive to factor. It's a difference of two squares after all. So we're going to go ahead and factor x minus 2, x plus 2. And what you're going to notice is that it does simplify with the denominator. Remember, when the factors cancels, that's talking about a gap. So that kind of matches our notion of 0 over 0 being a gap. Now, what's left over is x plus 2, which is a line with slope 1 and y-intercept 2. Now, it would seem a little bit troublesome to think that this rational function is exactly like this line. So let's take a look at a visual with decimals.com. We're going to look at the graph. So let me set that up for you. Okay, so we're here on decimals.com. I've graphed the rational function that was given to us, and it does in fact look like the line x plus 2. If I graph the line x plus 2, you'll see it turns blue because it is exactly the same graph. The difference, though, is that this first function has a restriction at 2. If I click on 2 here, we'll see that it is actually undefined, 2, undefined. So there is no y value there. If I bring up my x plus 2 line and click there, there's actually no problem, 2, 4. So what we learn is that these two graphs are identical at every point except when x equals 2. One has a gap, one does not. And I'm going to go ahead and show you the tables of values of those so you can see that the table of values actually confirms that. We have the same y value, undefined for 2, same y values, 4 for 2. So let's go back to our notes and make a note of that. If we go to this top graph I have here, I'm going to go ahead and call that f of x equals x squared minus 4 over x minus 2. And I'm going to put a gap right where that point 2, 4 was supposed to be. So we remember that's actually a gap. And then right below is the same exact graph. We're going to call that g of x. And that's actually x plus 2. But at 2, 4, there's no gap. So we're going to put a close point there. So what does this mean for us? It means that if you take the limit as x approaches 2 for g of x, you're going to get 4. And if we take the limit as x approaches 2 for f of x, you're also going to get 4. So how are we going to do this out? How is this going to help us algebraically? Well, if we know that these two functions have the same limit, not the same y value, we can use the limit of the simplified version to find the limit of the original rational function. And since we're not looking for the actual point at x equals 2, we don't really care that one has a gap and one doesn't. We'll just look at the behavior around that. So going back to our problem, what we'll do is we'll take the limit as x approaches 2 of the simplified version. And we know that that is, of course, 4. And because the limit as x approaches 2 of the simplified version is 4, we know that that's the same as we know that that is the same as the limit as x approaches 2 of x squared minus 4 over x minus 2. So to write that and summarize that, here's what we've done. Since g of x equals 2 is identical to the rational function x squared minus 4 over x minus 2, except f2 of course, we can use the simplified version to find the limit. Okay? So let's do a couple more examples to make sure we got this. Do more math. We're going to do this by factoring. And factoring is not the only technique that we have, but it is one of the more basic ones that we're going to encounter. So we'll do more advanced ones later. Let's look at the limit as x approaches negative 5 of x squared minus 25 over x plus 5. And before you start factoring, it's really important that you first do direct substitution, because there's once in a while you're going to run into a problem where the limit that you're being asked to find is not necessarily the discontinuity. So you are doing more work by factoring. It will still work because the simplified version is the same as the original function for most of the points, but it's just more work. So you want to first try substitution. And in this case, you do in fact get 0, 25 minus 25. Negative 5 plus 5 is 0 as well. So this means do more math. We're going to try factoring first. X minus 5, x plus 5. And then we are going to divide that by x plus 5. Of course, we expected that to cancel because this means we have a gap. We'll then take the limit of the simplified version. Direct substitution should work. Negative 5 minus 5 is in fact a number that we can work with, negative 10. And so that means the limit of the original function will be negative 10. I'm going to erase this. You can just write it next to it if you'd like. But in the end, here's our answer, negative 10. Now I want to give you one more example just to make sure you are good with one and two-sided limits. This is a two-sided limit, but you can apply the same strategy to a one-sided limit. Let's take the limit as x approaches negative 1 from the right side of the function 3x squared plus 7x plus 4. And we're going to put that over x plus 1. Again, you want to try direct substitution first. This function is a little bit more complex than the one before, but ultimately factoring is going to help us just the same. If I plug in a negative 1, I get a positive 3, a negative 7, and a positive 4. That simplifies to 0. On the bottom, negative 1 plus 1, of course, is 0. So do more math. And we are going to go and factor that top. It's a little more difficult to factor, but you should be okay. 3x plus 4 times x plus 1. And I kind of expected the x plus 1 because I knew that they had a common factor. The 0 plus 0 was the hint. So I'll put x plus 1. They do cancel or divide out, and it leaves me with 3x plus 4. I will take the limit as x approaches the limit as x approaches negative 1. Let me fix that. X approaches negative 1 from the right side. And we're going to take it of 3x plus 4. It is a one-sided limit, but you apply the same strategy, which is direct substitution. That's going to give us 3 times negative 1, negative 3, plus 4 equals 1. So since the limit of the simplified version is 1, we can say that the limit of the original function is also 1. And that's pretty much it. This is our first technique for finding limits when the function is not necessarily well behaved at the point of interest. So what I'd like you to do now is take a moment and write your summary of what you have learned in this lesson. There will be a follow-up assignment on Canvas, so see you soon.